All right, guys, what did we learn yesterday? Linear algebra. What did we learn? We did many examples. Well, how do you find the solutions to linear systems or systems of linear equations? Elimination's one way, substitution's another way, graphing's another way, and then by integration. No, this last way was about through. It's like looking at it, interpretation maybe. Um, if the systems or the equations are multiples of each other, then it's going to have infinitely many solutions. So I think it's interrogation. No, interpretation. Yeah. So there's four ways to solve linear equations. All right, so we're looking at infinitely many solutions, right? Okay, all linear systems, linear equations can either have one solution, no solutions, or infinitely many solutions. That's it. No matter how many equations, no matter how many unknowns. All right, back to the infinitely many solutions. This had this had some. Okay, yeah. Some like vocab and stuff. So the parameters. So when if you want to prove something is infinitely many, one way to prove that there's infinitely many solutions is to basically solve for one variable, then set the other variable to a parameter, which is like an arbitrary value, and then show the parametric equations, which is the original equation that you solve for that variable, and then with the parameter in, and then what the parameter is equal to. And then if you set that parameter equal to random variables, or not variables, random values, plug that into the equation, solve for the other variable, and then solve for the original variable, you should just be getting solutions that make all statements true mathematical statements. For no solutions, you're going to have a statement that it doesn't make sense, a mathematical statement that's not true. Infinitely many solutions, you have a mathematical statement that is true without variables. Or you can show with parametric equations. And yeah. Okay, that's a little confusing. All right, but we'll continue. We got into augmented matrices and like elementary something forms, something transformations, something along these lines. Uh, the augmented matrix is basically like you take equations or statements and you put them into a matrix. So we're looking at augmented matrices for linear equations or systems of linear equations, and we want to have them all in the same order, in which they are basically an order of like constant variable, first variable, plus constant second variable, plus constant third variable, equals b. We want to have them in that form, and then have all of the other system or equations in the system also lined up like that in that form. All right, I think that's basically it. All right. Okay. Wow. All right. I guess we're in this historical note. So I'm gonna read this historical note, and then I'll be back in a second. Wow, guys. Well, we've done it. We finished reading section one. The historical note was about Maxime Boucher, American mathematician, and also just kind of like a polymath guy. First guy to use the term augmented matrix, as far as we know. The actual term, that was 1907. First time we've actually seen someone use an augmented matrix would have been back in about somewhere between 200 BC, 100 BC, China. Okay. What else did we talk about then? So elementary row operations. So basically, when we're solving linear systems, we're basically trying to algebraically manipulate the equations in a way that we don't actually fundamentally change them. We're just shifting them, but keeping the same underlying meaning to reveal the underlying solutions. Well, we do the same thing for augmented matrices, and we use the same operations just in matrix forms, and these are called elementary row operations. And this is like multiplying or dividing a row by a constant, adding one row to another row, subtracting one row to another row, substituting variables, etc. What were they actually? Three. Multiply a row through non-zero constant. That's what we just said. Interchange two rows. That's what we missed. Interchange two rows, and then add a constant times one row to another. Okay, basically what we said. Yep. Interchanging rows is what we missed, but we're going to learn, I think in the next section, we're going to learn actually how to solve these things. We didn't get really taught the order in which to do these. So I think they're called like Gaussian elimination. That's one way we're going to learn how to solve these augmented matrices and linear systems. So we officially finished reading this section. This would have been augmented rows and augmented matrices and elementary row operations, I believe, is this section. Yeah, and we're done now with reading the whole chapter 1, section 1, and now we're into the exercise set. So there are 1, 2, 3 pages of exercises. I'm just going to start trying to do one. So I'll be back to talk about what I did. So talk to you in a sec. All right, guys, so far I've been using basically interleave practice where I'll read, the question, and then I'll do one of those questions, then I'll move on to the next type of question. So I'm never mass practicing doing the same type of question over and over again. That's just a waste of time. So basically, I just did a few of these. 1A, B, and C, 3A, 4A, 5A, 7A, and then 9A. And I started checking my answers for all these. But I think starting tomorrow, I'll just do the problems, and then the next day I'll check my answers, because that's more in tune with the delayed feedback I've learned from Make It Stick. And so pretty simple so far. The first part was like asking, is this system or is this equation a linear equation or not? You're basically looking at what's being multiplied, or you're looking at the variables and making sure the variables only with power 1, not being multiplied by other variables or anything of the likes, not in the exponential or anything like that, or no trig in the variables. It can be roots, trig, exponentials, etc. if it's in the constant, but not attached to the variable really. Then we kind of did some translating from linear systems to augmented matrices and vice versa. We also checked if a specific solution is one of the solutions for a linear system by plugging in the solutions for the unknowns. Yeah, I think that's basically it. Writing a linear system in this form based on knowing that there's 2 unknowns and 2 equations, then translating that into an augmented matrices, our matrix, writing it. This one was like, I wrote it down, but it could be more accurately written like that. I don't know if this is backwards in the camera, but I guess I'll find out at some point. But yeah, basically, we're doing pretty well, I would say. This stuff is none of this is like, what do I do? It's like, okay, yeah, way easier than I thought. Probably means we learned the section well. And also it's a good resource. I mean, if it was too difficult, it maybe wouldn't be too bad, but this is fine so far. Easier than I thought it would be. I thought we were going to be working with proofs in this section. We're not working with proofs in this section. We're kind of just doing really, really simple linear systems and augmented matrix stuff that we learned. Okay. Yeah, tomorrow we'll probably just be mostly working on exercises. We'll see what kind of decision I make on how many of these practice problems to continue with before starting the next section, or vice versa, whatever. That's it for today. I'll talk to you later. See ya.